Hello guys, this is Code and Code and this is an introductory video for this course series number theory. So this is an overview of all the algorithms that we are going to study in this course. So let's start the lecture. So the whole course I have divided into two parts, part 1 and part 2. In part 2 we are going to study algorithms which are a bit difficult to study and which require a prerequisite, and all the prerequisite I've compiled into part 1. So first of all we'll be studying about primality test. So it is important to study this concept because prime numbers are being used in almost every algorithm, including Euler's Torsion function to Fermat's Little theorem. There are many algorithms which requires the knowledge of prime numbers, so it only makes sense to study about prime numbers and study about primality test. So in primality test we would be given a number and we have to tell whether the given number is prime number or not. After that we would be studying prime factorization. Of course, you are given a number and you have to find the prime factorization of that number. Suppose the given number is 100, so the prime factorization of 100 would be 2 raised to power 2 multiplied by 5 raised to power 2. After that we would be studying sieve of Eratosthenes. I don't actually know what is the actual pronunciation of this, so I will be referring this as sieve only. So we would be studying sieve, and sieve is a way to find out in a range the given number, whether the given number is a prime number or not. Suppose you are given a range, you are given q queries, and in each query you are given a number and you have to tell whether the given number is prime number or not, and you know the range of the query would be up to 10 to the power 6 or 10 to the power 5. You can't go and check again and again whether the given number is prime number or not, because the best method to check that is a square root n time method. So you can't every time go and check. For that you have to generate the list of prime numbers up to 10 to the power 6, and hence you can directly in constant time check whether the given number is prime number or not. So see, what it does is it generates all the prime number in a given range in n log n time. So we would be studying sieve, and then we would be having a look at binary exponentiation, which is also basis of matrix exponentiation. So binary exponentiation or fast exponentiation is a method in which we are required to calculate, which allows us to calculate a raised to power n in log n time. Suppose you are asked to calculate 23 raised to power 10 to the power 5, that is 23 or 23 raised to power a million. Then if you calculate it linearly, then you would see there are 10 to the power 6 multiplications. So the running time would be linear if you use, of course, brute force method. But if you use binary exponentiation, you can calculate 23 raised to power a million in log n time, that is log of a million, which is roughly 22 or 20. So it is, of course, as the time running time shows, it is a very fast way to calculate powers of a given number. So we would be studying binary exponentiation. After that we would be studying Euclid algorithm for calculating GCD, and then we would be taking a look at Goldbach's conjecture, which is a very little concept, so it won't take much time. And then we would finding the number of divisors of n. So you are given a number n, you have to find the total number of divisors of a given number n. And then we would be studying how we can calculate binomial coefficient efficiently. There are 3-4 methods by which you can calculate binomial coefficient. One is a linear in k, where you have to calculate nck. Another one which uses recursion is exponential, which utilizes the recursive definition of a binomial coefficient. And another one is where we use pre-calculate all the factorial and then if you have to calculate NCR modulo some prime number, then you can use Fermat's little theorem and then calculate the binomial coefficient if in constant time if you pre-compute all the factorials. And after that we would be having a look at segmented sieve. So we have already seen there is something called sieve of Eratosthenes, which allows us to generate the list of all prime numbers in a given range. Now a segmented sieve, what it does, it allows to solve a problem something like this. Let me show you this problem. So you are to implement sieve, what we need an array of size n. N is the number up to which we need to find prime numbers. So usually using sieve we take an array of size roughly of 10 to the power 6. But now in take a look at this question. This question asks you to generate a prime number in a given range m and n. So each time there are t queries. In each query you are given m and n. You have to print all the prime numbers in that range. For example, 1 to 10, you have to print all the prime numbers in the range of 1 to 10, and the prime numbers are 2, 3, 5, 7, of course. Now n and m can be as large as 10 to the power 9, as you can see. So we can't take an array of size 10 to the power 9, so that is a problem which cannot be solved using sieve. Now we modify sieve a little bit and then we call it segmented sieve. So you need to look for a special property. You can see here the number of element in the range, even though the ranges may range L and R, or basically n m n can range from 1 to 10 to the power 9, but still the number of L and R are designed in such a way that the number of elements between the range are not more than 10 to the power 5. So what we can do is we can apply segmented sieve. That is, we can take a segment of these numbers and for example we can if the L is like 1000 to 2000, then we can give index 0. We can take index 0 as 1000, index 1 as 1001, and index 2 as 1002, and so on. So that way we can still take an array of 10 to the power 5 and then apply segmented sieve. I will tell you how we implement it, and then we can apply the normal sieve to solve or to find all the prime numbers in that range. So after studying segmented sieve, we'll be studying about modulo inverse, which is one of the most important concepts in modular arithmetic. So this is basically part 1. Now in part 2 there are concepts which are a little bit tougher than the previous ones. So after studying Euclidean algorithm, we would be going for extended Euclidean algorithm. Extended Euclidean algorithm is used to calculate inverse, modular inverse, as well as to solve Diophantine equation. So have a look at this equation. So I hope you can see. So the question says, from Euclid it is known that for any positive integer a and b there exists an integer xy such that ax plus by is equals to d, where d is GCD of a and b. So the problem is you are given t test cases, and in each test case you are given a and b. So you can see here we are given a and b. There are 2 test cases. In each test cases we are given a and b. So we are given a and b. We have to find their GCD, that is d, x and y, which satisfy this equation. So this is basically a linear Diophantine equation. You can study more about it, just Google it. So we are given a linear Diophantine equation, and we have to tell this we are given a and b, that is coefficient of x and y, and we have to find their GCD, that is d, and x and y such that the equation ax plus by is equals to d satisfies. So if you take the GCD of 4 and 6, it is 2, and hence 4 multiplied with -1, so -4 plus 6 is equals to 2, which satisfies this equation. So we have to print x, y and d which satisfies these equations. And there are also some constraints or what values of x and y we have to print, because there are many solutions which exist for this equation. So we are given certain restrictions on the values of x and y as well. So what I want to say is that extended Euclidean algorithm is also used to solve linear Diophantine equation and also to calculate inverse modulo, if of course the inverse modulo exists. After studying that, we would study about matrix exponentiation. Matrix exponentiation is basically calculating given a matrix, calculate its power to n. That is, you are given a matrix A, suppose, and you have to calculate a raised to power n. Then we use matrix exponentiation, which is basically fast exponentiation on matrix. After studying that, we would be looking at how matrix exponentiation can be used to calculate Fibonacci numbers in log n time. And important thing is that Fibonacci numbers are actually recursively defined, or these are recurrence relations. So any recurrence relation can be solved using the nth element of any recurrence relation can be found using matrix exponentiation in log n time. So just have a look at this problem. First of all, we would study about matrix exponentiation. So you are given t test cases. In each test case, you are given two integers n and m, and m the size of the matrix and n to the power to which we have to calculate. So we are given a 2 cross 2 matrix and we have to calculate it power up to 3. So basically, if I call this a matrix A, then we have to calculate a raised to power 3. And since n and m can be very large, m the number m cross m, that is the matrix size, can be as large as 50 cross 50, and n can be 10 to the power 5. We cannot calculate it in linear time because matrix multiplication is actually n cube operation. So if we have to perform, like if you are given n cross n matrix, then a single multiplication of 2 n cross n matrix takes n cube time. So if we have to perform 10 to the power 5 multiplication, if we are going to solve the problem brute force way, then there are 10 to the power 5 multiplication that we have to perform. There are 10 test cases and 50 raised to power 3 operation per multiplication. So this would be out of time, of course, and you would receive a TLE if you use normal multiplication method. So we would study how matrix exponentiation, or basically fast matrix exponentiation, can be used to calculate higher powers of a matrix in a very fast way, like n cube log n time. N cube, if the matrix size is m, then m cube log n time. And yeah, if you are solving any problem of Spoj or anything, then you can simply go into the comment section, and there may be people who tell, if you do not know what algorithm or something to use, then there may be people who actually tell what algorithm you can use to solve this problem. And yeah, this is also a problem which can be solved using matrix exponentiation only. Now after matrix exponentiation, we would be studying Chinese remainder theorem, and then Euler-Stoichern function. This is one of my favorite topics though. So let me show you the problem that you can solve using Euler-Stoichern function. By the way, Euler-Stoichern function, or ETF, of a number n is equals to the number of integers from 1 to n such that their GCD with n is equals to 1, or basically they are co-prime with n. So ETF of 6 is equals to 2, because from 1 to 6 there are only two numbers which have GCD 1 with 6. So 1 and 6 are having GCD 1 with 6 is having GCD 1, 5 with 6 is having GCD 1. So in range 1 to 6 there are only two numbers, 1 and 5, which are having GCD 1 with 6, or 1 and 5 are co-prime with number 6. So ETF of a number n is equals to number of elements in range 1 to n such that they are co-prime with number n. So this is Euler-Stoichern function. And look at the problem. This is one of the problem that you can solve using Euler-Stoichern function. And the question says you are given t test cases and you are given a, b and n. So you have to calculate summation I ranges from 1 to n, summation j ranges from 1 to n. You have to calculate summation of this GCD of a raised to power I minus b raised to power I, comma a raised to power j minus b raised to power j. So we have to solve this problem. Now this problem is very special because this is one of the problem that were asked in ACM ICPC Kolkata regional contest, and as you can see, this is the hard problem from Code Chef. So after studying Euler's torsion function in detail, we would be able to solve problems like these. After studying Euler's torsion function, we would be studying this is relatively easy concept, sum of divisors. You are given a number n, find the sum of the divisors of n. And then we would study Pollard p minus 1 and Pollard row algorithm of integer factorization. You might think that in part 1 also we had integer factorization, and now here as well. Now Pollard p minus 1 and row are different from those algorithms because first these are actually probabilistic function, because there are probability that these function may not actually factorize the given number. They work on probability like 90% or something, and these are the algorithm that we know which are 100% sure that they would factorize the given number. The best algorithm can be used to factorize number n in square root of n time, but Pollard p minus 1 and Pollard row algorithm are much faster than that. Because just look at this question. Now this question asks you to find the integer factorization of the given numbers. So as you can see, the second last number, this number, has prime factorization this. Now the input can contain integers which are having as large as 20 digits. Now if you take if there are 20 digits, which means the number is 10 to the power 20 up to 10 to the power 20. Now if you take the square root of it, it is 10 to the power 10. So if we use the traditional method to factorize the numbers, then we have to run a loop till 10 to the power 10, and which would result of course in TLE. So we can't solve this problem in using the traditional method. So we have to study Pollard row algorithm and Pollard p minus 1 algorithm to factorize the numbers. And same goes for this. As you can see there in this problem, the question is same. You are given an integer and you have to find the prime factorization of that number, but now the digits that is the input number can be as large as 10 to the power 30. If you take its square root, it is 10 to the power 15, sorry. So you cannot even imagine to run a loop from 1 to 10 to the power 15 to find the factorization of the given number. Of course, to solve those problems, we need some algorithm, integer factorization method, which are way faster, and Pollard p minus 1 and row are exactly the same. So these are the algorithms that we would be studying in the whole course. It would be a long one, of course, so bear with me till the end of this series. So thank you guys for watching, and yep, keep coding. Thank you.